Hello, my name is Kendall Shepherd, and I will be presenting to you today endurance performance and energy metabolism during exercise in mice with a muscle-specific defect in the control of branched-chain amino acid catabolism. Introduction. This research was conducted to examine the effect of uncontrolled BCAA catabolism on endurance, exercise performance, and skeletal muscle energy metabolism on muscle-specific BDK deficient mice, BDK MKO mice. Untrained control and BDK MKO mice showed the same performance, but the endurance performance enhanced by 2 weeks of running training was somewhat but significantly less in BDK MKO mice than in control mice. Skeletal muscle had low levels of glycogen in the BDKO MKO mice. Introduction, review of literature. Metabolism. The total of all cellular reactions that occur in cells and includes chemical pathways that result in the synthesis of molecules, anabolic reactions, as well as the breakdown of molecules, catabolic reaction. Energy metabolism, the processes that underlie food intake, burning the food to release energy, and storing the excess for the time of energy. Process of generating energy, ATP, from nutrients. Exercise, a subclass of physical activity. Activity requiring physical effort carried out especially to sustain or improve health and fitness. Introduction, review of literature continued. Catabolism, the breakdown of complex molecules in living organisms to form simpler ones. Together with the release of energy, destructive metabolism, branched-chain amino acids, a class of essential amino acids that the body can use for energy and muscle synthesis. Branched-chain amino acids comprises 35% of the body's protein. BCAAs also boost immune function, stimulate fat loss, increase recovery. They also are anti-catabolic effect, and they also promote endurance. Endurance, the ability to withstand stress over prolonged periods of time. Essential amino acids consist of leucine, isoleucine, and valine. Introduction. Branched-chain amino acids are made up of essential amino acids, leucine, isoleucine, and valine. BCAAs are unique in their catabolic system. They are catabolized directly in skeletal muscle, whereas EAAs are catabolized in the liver. BCAA catabolism is based off the activities of the first two enzymes, which are prevalent in the three types of BCAAs in the catabolic pathway. The first enzyme is a branched-chain aminotransferase, BCAT, which catalyzes transamination of BCAAs to produce corresponding branched-chain alpha-keto acids, BCKAs. The BCAT activity is quite high in the skeletal muscle, but the enzyme is not expressed in the liver. The second enzyme is BCKA dehydrogenase complex, BCKDC, which catalyzes the oxidative carboxylation of BCKAs to produce corresponding CoA esters. BCKDC's activity differs from BCAT. They are low in skeletal muscle but extremely high in the liver of rat and mice. Oxidation of BCAAs in skeletal muscle is regulated by BCKDC. BCKDC is regulated by covalent modification. The enzyme is inactivated by phosphorylation of the E1 alpha component of the complex and is activated by dephosphorylation. BDK in rat is very high compared to that in liver, which contributes to very low activity of BCKDC in skeletal muscle of rats under normal and resting conditions. Endurance exercises enhances expenditure and promotes the oxidation of protein and amino acid breakdown. Exercise enhances BCAA oxidation and increased BCKDC activity in human and rat skeletal muscle and rat liver. BCAA chronic supplementation improved endurance performance, likely through enhancing protein synthesis and mitochondrial biogenesis in human and mice. No research has been conducted to examine the effects of promoted BCAA catabolism and BCAA deficiency in tissue and exercise performance. The high BDK activity in muscle tissues suppresses BCAA oxidation. However, the mice with muscle-specific BDK defect had high muscle BCKDC activity, resulting in the promotion of BCAA oxidation. Problem hypothesis. To see how BCAA catabolism would affect mice endurance during exercise and skeletal muscle energy metabolism. How will BCAA catabolism affect the endurance performance and skeletal muscle energy metabolism? Methodology materials. Ethics statement. All procedures were approved by the Animal Care Committee of the Nagoya University Graduate School Bioagricultural. Mice. The animals used are BDK MKO mice using the Cree system. The mice were mated with transgenic mice that had the Cree recombinase gene driven by a muscle creatine kinase promoter to generate BDK MKO mice. The control mice were housed with lights on from 8 o'clock a.m. to 8 o'clock p.m. At 4 weeks of age, the male mice were weaned and housed individually. The new housing arrangement allows the mice free access to water and standard rodent chow. Beginning at 8 weeks of age, the male control BDKO mice were precisely fed an experimental diet until the end of the experiment. At the end of 11 weeks of age, the endurance capacity of all the mice was assessed by measuring the distance of running a motor-driven treadmill with a 10% grade. The running speed of the test was an initial 15 meters per minute for 4 minutes, which was then increased at a rate of 1 meter per minute every 4 minutes. All of the mice until 14 weeks were trained for 2 weeks by running on a treadmill with a 10% grade for 60 meters per day at a speed of 15 meters per minute in the initial week 1. The second week speed was increased to 18 meters per minute, both with a frequency of 5 days per week. The endurance capacity of all the mice was assessed again using the same method 2 days after the last running training. The same set of mice were also prepared for the metabolome analysis. They also were introduced to the swimming at 12 weeks of age. They were accustomed to swimming 10 minutes per day for 2 days. After being introduced to swimming for 4 days, the endurance rate was evaluated once a day for 4 days. Metabolic extraction and metabolome analysis were conducted. Approximately 50 milligrams of frozen tissue was extracted. The tissue was homogenized and then centrifuged. Metabolome analysis was conducted using the basic scan package HMT with capillary electrophoresis, time of flight mass spectrometry. Peaks were normalized based on internal standards, levels, and sample amounts in order to obtain relative levels of each metabolite. Results. Running distance to exhaustion before the exercise training was not different between the control and BDK MKO mice. After 2 weeks of training, both groups of mice ran more than 2 times greater than the distance that before training. However, the running distance was significantly less in BDK MKO mice than in control mice. The results showed that the swimming time tended to be increased in control mice, but not in BDK MKO mice, resulting in significantly less swimming time in BDK MKO mice than in control mice on day 4. This graph basically shows what I just described. So here, you can see where the running distance is similar before training and it's slightly different after training. Here, it displays the different swimming between the 4 days, and you see how it ranges from before training and after training. In BDK MKO mice, BDK was detected in the heart and skeletal muscle, but was seen in other tissues. The amount of subunits of muscle BCKDC were not affected by exercise in either of the groups of mice. The concentrations of the 3 plasma BCAAs were significantly lower in sedentary BDK MKO mice than in sedentary control mice. The concentrations tended to be decreased after the exercise bout in control mice, but the opposite was observed in BDK MKO mice. The increases in plasma BCAA concentrations in BDK MKO mice might be related to the increases in the amino acid concentrations in tissues other than muscles such as liver. The concentrations of other plasma amino acids were not different between the sedentary control and BDK MKO mice, except that the aspartate concentration tended to be higher in BDK MKO than in control. Since muscle glycogen content had been reported to be a factor affecting exercise performance, we determined that contents in the hind limb muscle glycogen content was significantly lower in sedentary BDK MKO mice than in sedentary control mice. The exercise bout significantly decreased the glycogen content in both groups of mice, resulting in lower glycogen content in BDK MKO than in the control mice after the exercise bout. BCAA and their metabolites. The levels of the 3 BCAAs were significantly less in BDK MKO mice than in control mice, and with and without the exercise bout. Specifically, leucine and isoleucine levels were less than half in the former compared to the later. The concentrations in both groups of mice were not affected by the exercise bout. The levels of alanine, aspartate, glutamate, histidine, lysine, and threonine tended to be higher in BDK MKO mice than in control mice, but were not affected by the exercise bout. This figure here shows the glycogen contents in skeletal muscle of control and BDK MKO mice with and without the exercise bout. Significant difference between control and BDK MKO mice. Significant difference in the same group of mice with and without the exercise bout.